Okay, today we're going to be looking at the limit of friction. So, we've already been learning that when an object is in limiting equilibrium, or at the point of slipping. So if say we've got something on like a box on a ramp and it's just about to slip down but not quite, friction is at its maximum. When an object is moving, so when we've got an object moving, we have a wee car here. When the car's moving at a constant velocity, when object is moving, friction remains at a limiting value. And that limiting value is F is equal to our coefficient of friction times the normal reaction force. So the normal contact force. And we saw earlier that the friction is part of the total contact force. I'll just write it down here. The total contact force was the normal contact force squared plus the limiting of the value of friction, its limiting value squared, all square rooted. Now, if an object is moving it, is accelerating, so say we've got our car again. That's a terrible wee car. Let's try there we go. It's moving, but now it's accelerating. The acceleration is going to be parallel to the surface. So acceleration is parallel to the surface. And that can be the same as, say we've got our little car and it's accelerating. So it's down the slope. It can go up the slope. We're going to say it's accelerating down the slope. This acceleration will be along the line of the greatest slope. So at some angle theta, acceleration is parallel to the greatest slope. So it's parallel to this slope coming down here. If we resolve the parallel to the surface, we find the acceleration. We will not find the solution. We will not find a solution because the size of the friction is not known. So in this situation, we don't know the size of friction. Friction depends on two factors. Firstly, the coefficient of friction, and R, the normal contact force. So we need to, when we're dealing with the slope, we need to work out the perpendicular and parallel elements of the force in order to find what the acceleration will be. We'll write all that down. So, in order to calculate the acceleration in the direction parallel to a rough surface, we resolve perpendicular to the surface firstly, we'll do it first, to find the normal contact force and hence the frictional force. Then resolve parallel to the surface to calculate acceleration. And we use Newton's second law, F equals ma. Now, previously, so this is essentially what we're going to be doing today. Previously, we thought, if you remember in the last video, we were thinking about this car on a slope. And we didn't know which way friction was acting. So we needed to know how to deal with situations where we didn't know if the motion, we didn't know if there was going to be any motion or not. So if we think about this car and it's held by a rope, and it might not be moving, or it might be about to move, and which way is friction acting on it. And so we need to calculate different situations. When you're not quite sure, start by looking at the situation. When unsure of the direction of friction, consider the most likely scenario, and then see if there's any contradiction. Then see if there is a contradiction. We'll show you what that means in a minute. So let's consider the same. Let's open it. Oops. So let's consider our same car, and we're going to do some. And it's being pulled up the line of greater slope. This time we don't know whether the car remains stationary or not. So it's been pulled up here, and we don't know if it's stationary. If we assume the car slips down the slope, so if we're assuming it's slipping down the slope, friction must be limiting. If we assume it's slipping down, then friction must be limiting. However, if acceleration is negative, then this contradicts the assumption. So say we had all our figures and we were assuming that the car is slipping down here. So we're assuming acceleration is in this direction. But say we get a negative acceleration, well that is contradictory, because if it's sliding down the slope it'd be speeding up and acceleration would be positive. Therefore we've got it the wrong way, and the motion must be therefore up the slope. So we would therefore go through the same steps again, but then with a different direction of motion, and that would then fix the problem. So if when you're doing this, if you've made the wrong assumption and you get a negative acceleration, then you need to change your initial assumption and change those things on the force diagram that need to be changed, and it should all work itself out. So let's look at a couple of examples, because these kind of things can sometimes not be plain until we see them actually happening. So we've got a curling player. If you don't know what curling is, it's a winter sport where you get a big shiny stone and you slide it along ice, and it's a bit like bowling on ice. Probably not the best analogy, maybe curling players would disagree. If you're not sure where it is, Google it and you'll have a wee look. A curling player tries to slide a curling stone of mass 20 kilograms along a horizontal ice rink. To stop on top of a target that is 46 meters away from where it is released. The coefficient of friction between the ice and stone is 0.05. The player releases the stone with a speed of 6.5 meters per second. Find how far the target, how far from the target it stops. So let's draw our force diagram. So here's our ice, here's our curling ball, and we're told it has a mass of 20 kilograms, so the weight coming down here is 20 g. Now it's going in, this is the direction, write your direction of motion in. And its acceleration is in this direction, in the same direction of motion. So we have friction acting against it, and it's got the coefficient of friction times R. So that's our first diagram. Now, first we need to find our normal contact force. So we resolve vertically first, or we've got to put our normal contact force, R. So we're resolving vertically, and because it's on the horizontal, the motion, R is going to be 20 g, so 200 newtons. And now we're going to, so it's resolved vertically. Next we're going to resolve horizontally. So we've got our friction in this direction, and in, so we're going to use, for this, we use F equals ma. So our coefficient of friction times the normal contact force must equal 20 A. This is negative, so A must be, putting our numbers in, minus 0.5 meters per second, which makes sense because it's been released with 6.2 meters per second and it's slowing down to come to a halt. Now, we're going to use our equations of motion. So we're going to use v squared equals u squared plus 2as to find how far the curling ball is going to go. So our final speed is 0 because it comes to a halt. It's released with a speed of 6.5, that's going to be squared, plus 2 times minus 0.5 s. And working all that out, we get s is 42.25 meters. Now, the target is 64 meters away, so the distance from target is 64 minus 46, sorry, minus 42.25, and that is 3.75 meters away. So it's not quite close enough. So we're now going to go to our second part of our problem. And in the game of curling, you've got sweepers. So those sweepers come and they polish the ice, therefore reducing the coefficient of friction. So sweepers sweep the ice and reduce the coefficient of friction, assuming they lower the friction equally along the path. Find the reduced coefficient of friction. So we're going to use our, I'll do it up here. So again, we're going to use v squared equals u squared plus 2as. Again, it's 0, and this initial speed hasn't changed. This time we don't know what A is going to be. 2 times A, now S this time is 46 because we want it to go all the way, and that then gives us a value for A, which is minus 0.459 meters per second squared. So as before, we know that the normal contact force is still 200 newtons because that's not changed. And from the Newton's second law, F equals ma, so minus mu r must equal 220a, which gives us a new coefficient of friction as 0.0459. Now, we're going to do a more tricky one. A woman drags a box of mass 20 kilograms up a rough slope. A little tip for exam questions: if you see the term rough slope, you know you're going to have to do some stuff involving friction. The slope is at 10 degrees to the horizontal, and the coefficient of friction is 0.45. The woman pulls the box with a rope which is held, a rope at angle 20 degrees above the slope, with tension, which we'll call T, equal to 120 newtons. Find whether the force is large enough to create motion, and if so, what is the acceleration? So the first thing to do is our force diagram. So we've got our wedge, and that's 10 newtons. Then we've got our box, and we've got this, we do a wee dashed line parallel to the slope, and we've got this rope here, and it's 20 degrees up here, and that's tension as 120 newtons. Now, we've got our normal contact force R, and we've got the weight of the box coming down here, and that's 20g. And then let's assume friction is going to be coming down the slope, and it's mu times normal contact force. So we're assuming this direction of motion up the slope. So firstly, we're going to resolve perpendicular. So the perpendicular, we're going to have perpendicular to the slope, we've got R, plus the perpendicular component of this rope. So think about perpendicular to the slope is going to be 120 sine 20, and that must be equal to 20 g cosine 10. Now because the friction acts parallel to the slope, there's no component of friction in the perpendicular. So we can use this to find out that R is 156 newtons. Now we're going to resolve parallel to the slope. So this is using Newton's second law, and we have 120 cosine 20 minus, so that's the force in this direction pulling up, but then we've got the force, the weight pulling down, so that's going to be minus 20 g sine 10 degrees minus the friction, and that must be equal to the mass times acceleration. And if we put everything that we know in, we'll find A is equal to 0.393 meters per second. Now, all squared. Acceleration is positive, therefore our assumption of motion up the slope is correct. The tension in the rope was great enough. Had we got a negative acceleration, then we'd be able to say that the force in the rope, the tension in the rope, is not strong enough to create motion up the slope. So the box wouldn't be going up the slope at all. So I hope that helps.